We've seen recently that we can use fork to create multiple processes, and that those processes can run simultaneously, and that the operating system manages switching between them. Since modern computers tend to have many CPU cores, we'd like to take advantage of this multiple streams of execution in order to accomplish tasks faster. And while fork and exec are great for accomplishing multiple separate tasks at the same time, they're not particularly good at speeding up an individual task. Specifically, communicating between different processes is quite clunky, as we've seen with signals. And so if there's a task that we'd like to speed up by executing on multiple CPU cores, but that we can't break up into completely separate operations that can be run by different programs, then we'd like some way of having parallel streams of execution within a single process's address space. And this can be accomplished using threads. Threads give us a way to create multiple streams of execution that can take advantage of multiple CPU cores and the operating system's context switching mechanisms, but those streams of execution operate within the address space of a single process, which makes collaboration between the different threads much simpler. Here we have a simple program that we can use to demonstrate splitting up work among multiple threads. The work that we're doing here for demonstration purposes is extremely simple. We are just incrementing a variable a large number of times. And right now, this program is single-threaded, just like all of the programs you have written in C so far, where we have a main function that reads some command line arguments and then calls our incrementer function, passing in a pointer to the variable that we want incremented, and then the number of times that we want to increment it. And this serves as a proxy for real work that a more interesting program might do. So let's compile and run this program to see how long it takes. We run this program with one command line argument, which is the total number of iterations, and I'll give it 10 billion. And since we're interested in how long this takes to run, we can use the Unix utility time to see how long our program runs for. So for our single-threaded program, it took about 20 seconds to count to 10 billion. Now let's take a look at a multi-threaded version of this program. I've included the pthread library, which is how we create threads in C. And at the top here, we have the same incrementer function, but the rest of the program is more complicated. The main function begins similarly, processing some command line arguments, but now we have an additional argument for the number of threads. And we again have a local variable in main that the incrementer function will point to and update. But then we have a loop that executes num threads times and creates the worker threads that will do the incrementing. We create worker threads with the pthread create function, and pthread create takes a very specific set of arguments. The first argument to pthread create is a place where the pthread create function can place the ID number that it gives to the thread. And we have allocated an array of pthread t variables where we can, for each thread, allow pthread create to put the ID number that it creates into the ith element of the array. The next argument is used for changing the settings of pthread create, but since we're okay with the default settings, we can give it a null pointer. And then the last two arguments are how we actually start each of the threads. This third argument is the function that we want the thread to use as its main function. And so we have written a function up here called thread main, and we are passing the name of that function as the third argument to pthread create. The last argument to pthread create is a pointer to the argument that will be passed as input when the thread main function is called. So let's take a look at the manual page for pthread create to see what's going on with the thread main function and its argument. In the type signature for pthread create, the third argument, this start routine, has a very complicated type. What these types mean is that we are giving a pointer to a function, which we do by passing the name of the function, and that function has to be of a very specific type. It has to take a void pointer as input, and it has to return a void pointer as output. A void pointer in C is a pointer that is allowed to point to any type of data. And so, by taking a void pointer as input, we can decide what sort of thing we are going to give as the input pointer to our thread main function. And by returning a void pointer at the end, the thread main function can give back a pointer to any type of data. And this last argument is of type void pointer, and so that is the thing that will become the void pointer argument that is passed into the main function for the thread. So if we look at our thread main function, its signature matches with the type of thing that we can pass to pthread create. It takes a void pointer as its only argument, and it returns a void pointer. Passing a void pointer means that we can pass any type of thing we want, and in this case, we would like our thread main function to receive several different inputs. We would like it to know the pointer to the variable that it's incrementing. We would like it to know how many iterations it needs to run, and we'd also like to give it an ID number so that it can identify itself when we first create it. But since the type signature for pthread create forces us to give a single void pointer as the input, what we have to do is package up those three arguments that we would like to give to the function into a struct, which we can then unpack to get the arguments that we really wanted. A struct in C is a way of packaging up several different pieces of data into a single value that we can pass around. If you've used a language like Python or Java that has objects, a struct is kind of like a class, except that there are no methods associated with a struct. It only packages up data. And so here we've defined a new type of struct, which is called thread args, and we're using this thread args struct to pass three values as input to the main function for the thread. So to give these three arguments into the start routine for the thread, we have to, before creating the thread, package these three things up into a struct, and then give a pointer to that struct as the input to thread main. So let's take a look at our thread creation loop and see how we're packaging up those inputs. Here in the main function for our thread increment program, we have an array of type thread args struct, and this array contains num threads elements. And so, when we are looping to create our threads, before calling pthread create, we are first filling in the ith element of the args array by setting the toIncrement pointer, the numIters long, and the thread ID int. So we package up the three things that we wanted to pass as fields on the struct, and then we pass to pthread_create a pointer to the struct that we just packed up. So that means that when thread main is called, the input that it receives will be a pointer to the ith element of this array, which is the struct that contains the three inputs that we wanted to give to the start routine. Then, in the thread main function, we start by casting the void pointer that we were given to make it a pointer to a thread args struct, and then we unpack the elements of that struct into the local variables of our thread main function. Once we have unpacked this struct into local variables, we can then do the actual work in the thread. So here we are calling the incrementer function and asking it to increment the pointer the appropriate number of times. And then at the end, since we didn't need to return anything, but our return type was void star, we have to give back a pointer, so we'll give back a null. Back in the loop where we were creating threads, note that we are setting the number of iterations for each thread to be the total number of iterations divided by the number of threads. And so we are looping num threads times, and each time creating a new thread that has been assigned an equal fraction of the overall work. Finally, once our main function is done creating all of the threads, we have another loop that calls pthread_join for each of the threads. This call to pthread_join takes as input the pthread_t that was assigned by the pthread_create function. So this is an internal thread ID that was given to the thread by the pthread library, as opposed to the ID starting from 0 that we gave to the thread manually. But with that thread ID, we can have the main function wait until the thread has completed. And so we are having the main thread wait for all of the worker threads to finish their work before we print out the resulting value and exit. So in total, we will have called pthread_create as many times as we requested threads, and each of those will be assigned an equal fraction of the overall work, and then each of those threads will start with this thread main function that will unpack its arguments and then call the incrementer function to do its share of the work. So let's try compiling and running this multi-threaded version of the program. Notice that in the compilation command we have linked the pthread library. And now we can tell it how many threads we want to split the work among. While this is running, let's draw a stack diagram of what's going on. Initially, we have a main function which has, among other things, our variable that we're incrementing. And it also has the array of thread args structs that we've set up. And that struct has several fields, including the ID of the thread and the pointer to increment and the number of iterations. So this value here is 2.5 billion. So as main loops, it fills in the elements of this array of structs, and it also calls pthread create. What pthread create does is give us a new thread that is executing on a new stack. So in our stack diagram, on the first iteration, we will get a new stack where the base of that stack is the function that we asked pthread create to use as the start routine for the thread. So the thread main function is on the bottom of this stack, and its argument was called Args pointer. And we gave as that argument a pointer to the struct that we filled in as the ith element of our array of structs. And so that pointer gives us a reference to those arguments that we packaged up in main. And so now when we access the elements of that struct, we unpack them into local variables that live in this stack frame. When we unpack the toIncrement pointer, that was a pointer to the local variable in the original main function, and so that pointer gets copied into a local variable. And the thread ID value from the struct gets unpacked into the myThreadID variable, and since this was the first thread we created, it was assigned the ID 0. But then on the second iteration of the loop, when we call pthread create again, we get another new function stack for the new thread that we are creating. And so this one also has thread main as the base of the stack, but now the args pointer that was passed in this time was a pointer to the second element of our array of structs. And so this way, on our second call to pthread create, we passed in a different set of arguments for this second thread, which can allow it to do different work than was assigned to the first thread. In this case, the only thing that was different about the arguments was that this one was given a thread ID of 1. And our main function continues, creating 2 more function stacks for the 2 additional threads, so that we have 4 threads total. But once we have created those threads, they are running as a separate stream of execution, and so the main thread and each of these worker threads can be executing in parallel. And so at the same time that the main thread is calling pthread create again to create our third worker thread, one of the previous worker threads might get to the point where it is calling the incrementer function. And the incrementer function has a pointer to the value that it is to be incrementing. And so each of the 4 threads that gets created will all have a pointer to this same location in memory that lives in the stack frame for the main function of the original thread. And so all 4 of the worker threads, when they are incrementing the thing that toIncrement points to, they are all modifying the same location in memory. And so each of these threads will perform their 2.5 billion increments, and then they will return, at which point the main thread can continue executing and print out the resulting value. But when we look at the result that we got when we ran our multi-threaded version of the program, a few things might seem fishy. We got the wrong answer. We didn't increment to 10 billion. We only managed to increment to about 3 billion. And the version with 4 threads took way longer than the single-threaded version that we ran originally. So what the heck is going on here? Well, to start with, we could see if maybe we implemented something wrong, or maybe the threading library just slows us down a whole lot, so we could try running our thread increment version with just one thread. And this time we got the right answer, and it took just barely longer than the original version of the program. So the fault here isn't that the thread library is slowing us down, or that we somehow incorrectly created the threads. The problem here is actually a much deeper one to do with what's going on when we run a multi-threaded program. Specifically, let's think about the line in our incrementer function that is adding 1 to this value. Just like when we have multiple processes, when there are multiple threads running in parallel, their execution can be interleaved in any order. And what that means is that when we are updating the place that is pointed to by toIncrement, each thread is retrieving the current value of that variable, computing that value plus 1, and then storing the result back into memory. And what can happen here is that one thread retrieves the value, and it sees a value of 0 in one of its registers, and it increments that value to 1, and then sends it back. But in the meantime, while that thread is retrieving and incrementing the value, some other thread might also have retrieved that value and see a value of 0, and now it has a 0 in its local register, which it will increment to 1, and then when it puts its value back, it will, rather than updating the one that was already there, it will just overwrite it. And it could also be the case that in the time that it took for this first thread to do one increment, this thread actually managed a couple of increments and put back the value 3, and then the first thread comes along and overwrites that with the value 1, having lost all of the progress that was made by the other worker. So that's how we end up with an incorrect value for our multi-threaded version of the program. So let's think about how we could avoid this problem. Well, rather than having each of the threads accessing this shared variable all of the time and potentially stomping on one another's updates, we could instead have each thread do its incrementing locally and then send the result back when it's done. So now each of the threads has a local variable which it will be using to do its share of the work, and then when it's done, it will one time retrieve the value of toIncrement, add its local value to it, and put it back. And so now, rather than having 10 billion different accesses to the shared variable, we only have 4. And this time we got the right answer, and lo and behold, we also got a much faster execution speed. So why is this version with the local variables so much faster? Well, the reason is that behind the scenes, the hardware is doing a lot of work to ensure cache coherency. When we have multiple cores in the same CPU, each of these cores has its own copy of the highest levels of the cache. And so if we have several CPU cores that are each accessing the same variable repeatedly, then we'll have a copy of that variable in the level 1 cache for each of these CPUs. And so if one CPU is accessing that data and writes to it, then that update needs to be sent to all of the other level 1 caches that have a copy of the data. And this can slow down our operations quite a bit. So in the version with a local variable, each thread is only accessing data that is local to its cache, and so we don't have to wait for that data to be sent to many other caches. And so all of the operations can be completed much faster. And so in fact, we could run with 40 threads, and on this computer, that takes us only around half a second, where the user time that is listed here is the CPU time that was used. So across the 40 different threads, each of them used around half a second, and so the total was around 20 seconds, and that's consistent in our previous run with 4 threads and in our original run with just 1 thread. But since we have spread that work across 40 different threads that can all execute simultaneously, the entire process completed in just over half a second. But also with 40 threads doing this work simultaneously, we now have a problem with a wrong answer cropping up again. And this is because when all of those threads are completing, it's possible that they will simultaneously access the value in the pointer, and one of them will overwrite the update from another. And so in fact, whenever we have multiple threads accessing the same data, there is potential for them to overwrite one another's results unless we carefully synchronize those threads. This could also happen in the version with just 4 threads. It's only that the likelihood of it happening increases the more threads we have and the more times we're accessing the shared variable. So to prevent this issue altogether and ensure that our program gives a correct result, we need to ensure that only one thread is ever completing this update at any given time. We want to make sure that the threads have mutually exclusive access to the shared variable that they are incrementing. And we do that using a type of variable called a mutex lock. We can declare a global variable of type pthread mutex t, where mutex here means a mutual exclusion lock. The idea of a mutual exclusion lock is that each of the threads can try to lock this mutex, and the mutex will ensure that only one thread at a time is able to acquire the lock. And so we can surround the sensitive bit of code that we need to ensure that only one thread at a time is executing with calls to pthread mutex lock and pthread mutex unlock. By including these 2 function calls in our incrementer code, we make sure that all of the different threads that are simultaneously executing this function, when they get to the lock line, only one thread will be allowed to proceed, because only one thread at a time can hold the lock. So the first thread to arrive will acquire the lock, and it will make its updates to the shared variable, and then it will release the lock. In the meantime, if other threads have arrived at line 14, those threads will be paused until the lock becomes available, and when the first thread unlocks the lock, then another thread will acquire it and be allowed to execute line 15 and then release the lock to subsequent threads. So by putting a call to lock before our critical section and a call to unlock after our critical section, we ensure that only one thread at a time is able to execute this critical section of code. And so now if we save, compile, and run, we get 40 threads executing simultaneously, and none of them can overwrite the results of another, and so we get the correct answer. Of note, this mutex lock variable is declared as a global variable, and this is one of the few times that it's actually a good idea to use global variables. Because each of the threads has its own function stack, it's much simpler to ensure that all of the threads have access to the same lock by making that lock a global variable. So in summary, we've seen that with threads, we can have multiple streams of execution running within the same process, meaning that they share an address space and therefore have an easier ability to share data and collaboratively solve a problem. This gives us the ability to write code that will take advantage of multiple CPU cores on a computer and solve a problem faster without having to break that problem down into things that can be done by completely separate processes. But we've also seen that when we write multi-threaded code, there's a lot more work that has to go into setting up the execution of multiple threads, and also ensuring that those multiple threads are collaborating in ways that give us correct results, where they're not overwriting one another's work, and also to make sure that we make efficient use of multiple cores in the CPU, where we're not copying data around between caches all of the time and wasting all of our CPU resources. But if we can come up with a good decomposition of our problem into work that can be done by the different threads with only occasional communication, and if we can ensure that the threads are unable to interfere with one another by using locks to protect the critical sections, then we can potentially dramatically improve the efficiency of our code by taking advantage of many cores in the CPUs of modern computers.